Good afternoon, good evening, good morning. My name is Peter Denning. I'm here hosting a series called Harnessing AI, and our job here is to help you understand this brand new field. It's not actually a brand new field, but to many people it's brand new, of this field that's suddenly having such an influence in our society. I'm a professor at the Naval Postgraduate School here. I'm in the computer science department. I've been around computer science, teaching computer science for many years, since the middle 1960s. And I've seen a lot of things come and go in the technology. And one of the things that's always been here in our technology in the background has been artificial intelligence since the 1950s. And it's had its growing pains and produced many interesting technologies that we use today. And some of these technologies have burst into public awareness in the last couple of years because of the appearance of generative AI, which is the new category of machines that will have conversations with us. So that we'll be discussing all these things in our series. Our objective here is to help you understand from the perspective of many different faculty members here what's going on in the AI field and see how it looks from different directions. So altogether we have 24 lectures in this series. Each of them is about half an hour, and each one presents the point of view of a particular professor who's an expert in that aspect, talking to you about how artificial intelligence looks in their area and how they see artificial intelligence. As you listen to them, you can expect different emphases. Some of them are more optimistic about the good that the technology can do, and some of them are more pessimistic about the good the technology can do. But they all agree that the technology here is here and we need to learn to live with it. So that's a background for our course, and I'm going to give you an introduction to the course now so you can see what kind of things are coming up in the lectures that are in the rest of this series. So we've called it Harnessing AI because we want to talk about how people can make use of this technology. So our purpose in the whole series is to answer some questions like, what is artificial intelligence? What is machine learning? What are their benefits? What are their risks? And in our context here at the Naval Postgraduate School, what is their military significance? As we do this, we also want to establish a common language and that we can talk about the different kinds of AI that exist and give us precise definitions of what we mean by artificial intelligence and machine learning. One of the aspects of this field since the beginning has been hype, meaning, as some of our lecturers will tell you, making big promises that they don't know what they can actually fulfill and then winding up later not being able to fulfill them. So what we want to do is show you where the hype is and cut through it so you can see what these machines, what these systems actually do. And then that'll give you a better grounding for putting them to good use. One of the things is in the background here is this little saying on the bottom here, don't mistake utility and speed for intelligence. These things are all run by computers. They go very fast, but the speed is not the same thing as intelligence. Now, the AI field has been around a long time. It was formally founded in 1956. That's when the name was given to it. And its purpose was to study how to build computing machines that perform intelligent functions. As this field has gone along over the years, it's been buoyed by enthusiasm, people finding new things they can do with these machines, and getting very enthusiastic about them. And at the same time, it's also been plagued by hype and overpromising, people thinking that these machines will be able to deliver more than they have actually been able to deliver. So you'll see this as our lecturers speak to you. You'll see the enthusiasm, and you'll see also the struggle with trying to get the hype out of the way. This little chart shows you the kind of conceptual view of the evolution of the field from its beginning in 1956 all the way through the present time. The chart shows the black wiggly line is a depiction of the level of interest in the field. And you can see that there was an initial period beginning when the field was started in 1956 where there was a growing interest, and then it sort of faded out, went down, crashed, if you want to say. Then it rose again, had another peak of interest, and it went down again. And then it in early 90s started to come back, and it's been coming back ever since. And today we're in a period of where the main technology that's gathering attention is called deep learning. And so far it's been going up, and who knows, it could go down again. We just don't know. These two periods on the chart where it went down seriously got the nickname winters, a name derived by analogy with the term nuclear winter, where it seemed like the whole field got leveled and nobody was interested, but then it resurrected. Underneath in the three columns, you see the names of technologies that were produced during these boom periods. So the early period of artificial intelligence focused on speech recognition, board games like checkers and chess, language translation, simple robots, problem-solving systems, early neural networks, and a form of neural network called a perceptron. In the middle period, a new boom came up, which introduced new technologies, including expert systems, knowledge revolution, multi-level neural networks, statistical inference, classification systems, sparse distributed memory, science grand challenges, strategic computing initiatives, and the fifth generation project in Japan. And then in the recent years, since around 2000, a little bit before that, we have new things coming in with data analytics, deep learning, image recognition, voice transcription, voice commands such as Siri and Alexa on your desk and at your home, grandmaster game players for chess and Go, human-machine symbiosis, driverless vehicles, automatic fire control, meaning automatic weapon systems, drone surveillance, both in the military and other places, swarms, which would be large groups of small vehicles like drones or ships acting together, and cyber defense and offense. So you can see over the years, a lot of different kinds of technologies has evolved out of this, and many of them are in use today and very useful technologies. But yet, if you ask people what exactly is AI, you have many different views pop up. The upper left view here is a picture of the famous Go tournament in Japan. I think it was 2016. You see the face there of Lee Sedol, the grandmaster, and he got beaten by this machine. Up until that point, people had believed that Go was such a complicated game, it was beyond the power of any computing machine to do better than a human Go player. Well, that event showed that we had constructed a machine that would beat the Go player. On the lower left, you see a picture of a smart speaker or microphone that you can find in your house, like a Siri or an Alexa. On the right, lower left, there's also a picture of a Terminator from a Hollywood film. And also on the the right side of the picture is a swarm of birds, and people think that swarms somehow have their own intelligence, a collective intelligence. So All of these things people seem to want to include these things in artificial intelligence if we can get a computer to do them. So we have to deal with that. Here are some popular notions of what artificial intelligence means. One of them is self-driving cars and autopilots. Another one is thinking machines, conversation machines, puzzle solvers, games, speech recognizers, vision recognizers, and expert systems. And these are all based on things that people can see, the technologies that are there that people can see and make use of. There's also a bunch of artificial intelligence notions given to us by Hollywood films: Terminator, Skynet, iRobot, Battlestar Galactica, Ender's Game, Commander Data, and R2-D2. So all of these are different kinds of impressions of artificial intelligence, ranging from extremely dangerous ones to, at the top of that list, to friendly, almost cuddly ones at the bottom. Well, there's many things that worry people about AI, and you read about them in the newspapers all the time these days. For example, we worry about automated weapon systems. Will somebody fire missiles based on a misimpression of an enemy's intent and cause great destruction? Or what about drone swarms being mobilized to be weapons of mass destruction? How do we master large battle spaces? There's huge amounts of activity going on over large regions and all sorts of different equipment and people. How do we manage that? When we deal with individual artificial intelligence machines, we get recommendations coming out of this. Sometimes we can't explain where they came from, and neither can the machine. So we worry about how reliable those recommendations might be. We have problems with neural networks. They can be pretty fragile. You can train them to do something, and then you ask them to do something new they haven't trained on, and sometimes they come up with unpredictable behavior. Another worry is mass surveillance and population control. This sort of thing appears in some countries. It also appears in novels and movies. Mass unemployment, another worry. Will these machines automate many jobs, and then people will be out of work? In recent times, we worry about generative AI, the large language models that can talk to us, and they tell us things, and we don't know whether we can trust them. And we don't know what applications we can put them into, especially if trust is an important issue. Another area of worry is deep fakes, which refers to images, voice prints, movies, videos that seem real. They seem to depict real people doing real things, but they're all artificially generated. And these things and other forms of disinformation worry people. And finally, the last thing here is a slang term: internet slime and data pollution, meaning that there's a lot of data that's in the internet that isn't reliable, in the sense it doesn't correlate to anything, but can be absorbed into artificial intelligence and mislead it. The term slime got introduced as a slang term recently because there's a lot of new content being placed in the internet by some of these generative AI machines, and it's becoming input to future machines as data, but it's slime in the sense that it's not based on anything. It was generated artificially. So those are things people worry about as they look at all these things. So when we come back to our question, though, what is artificial intelligence? Well, the usual definitions say it's computers doing human intelligent tasks. But the problem with that definition is you get left with, okay, what is intelligence? So what does it mean to do an intelligent task? So we're left with we come to the question, what is intelligence? Well, one of the big problems with intelligence is ill-defined. There's a lot of different definitions of intelligence, and nobody knows which one is superior, if any of them are. We also know there's different kinds of intelligence that are not really human intelligence. Most people will say ants and bees and dogs and cats, chimpanzees and other animals have different forms of intelligence. And in our own field, we have the problem of what's often called elusive goalposts, which means when we figure out how to get a machine to do the task, we think we have an intelligent task. When we get a machine to do that task, we no longer think of that as intelligent. Because we just say, well, a machine could do it, can't be intelligent. An example of that I grew up with was the quest for building a chess playing machine that could beat a world grandmaster. This took 30 years, but was accomplished in 1997 in a famous match with Garry Kasparov. He got beat by the machine. Well, as soon as that happened, everybody stopped thinking that chess was a symbol of an intelligent human being at work. It's just another thing a machine could do. So this adds to the complexity of trying to figure out what exactly is intelligence, and therefore, if we're doing it artificially, what does that mean? One thing we do know is this: intelligence is not speed. You can do something fast doesn't mean it's intelligent. Example with computers is machines can do 1 billion calculations a second, whereas we humans can only do about 1 calculation per second. So we never said computers were smart. Your laptop and your nearest supercomputer are not intelligent, even though they're fast. Can we get a scientific definition of intelligence? Well, many fields have been working on this, but they haven't come up with one yet. In fact, this idea that we have fields of science that are based on concepts that nobody fully agrees on is actually pretty pervasive. For example, artificial intelligence is a field that functions even though it doesn't have a precise definition of intelligence. Biology is a field that functions even though it doesn't have a precise definition of life. Neuroscience is a field, well-developed scientific field, even though it doesn't have a precise definition of what is consciousness. And computer science is also the central concern of computer science is processing information. Well, nobody has an exact definition of information. So a lot of fields have this problem, is that they deal with something which we can describe in a qualitative way, but we can't find a very solid scientific definition for it. And that doesn't stop progress in the field. So here's just a summary of what I just said. Artificial intelligence is interested in what is a machine intelligence. We have all sorts of questions like how to measure intelligence. Is it Turing tests? Is it logical reasoning? Is it associative memory? Is it natural language? Is it achieving self-determined goals? Or all those signs of intelligence? Is any one the earmark of intelligence? Nobody agrees. In the field of biology, the question of when is an organism alive? Well, biologists have made a little progress with that, but haven't come to a definite conclusion. They have a list of 7 or 8 things that are true for living organisms, but not necessarily true for every living organism. Here's a list: nutrition, respiration, movement, excretion, growth, reproduction, and sensitivity. The more of these things that an organism does, the more likely biologists are going to say that it's alive. If it only does 1 or 2 of these things, most biologists would say it's not really alive. Neuroscience. Neuroscience is interested in when is someone a conscious. So nobody knows how to define consciousness. So they have develop what they call correlates with which are observable features of somebody that would tell whether they're conscious. And these are of particular interest in places like hospitals when you're trying to decide whether a patient is dead or not. And then finally, in computing, the question is what is information? Because computing is supposed to be machinery that processes information. So is it symbolic information? Is it tacit information? Is it assessments? Substance of something? Is information a force of nature? There are physicists who say information is a force of nature, just like gravity, but there's a different force called information. So again, we don't have any definitive answers, but in all these cases, it hasn't stopped us from forming a science to study these things. Now, if we do literal interpretations of artificial intelligence and machine learning, we get a little further. We say AI means artificial intelligence, and what that means is designing intelligent machines, which are machines that can do things that we're familiar with intelligence, such as thinking and intuition, making conjectures, imagining things, expressing and carrying out intentions, making and keeping commitments, consciousness, cognition, self-awareness. So these are all kind of observable things, and the more of these observable things we can see in a machine, we'd say the more likely there's some sort of intelligence there. ML, machine learning, is narrower than artificial intelligence. Machine learning simply means that we're designing machines that can learn new functions from observing what's around them and from watching their own behavior. So with this, we can do things like speech recognition, image recognition, games, planning, deep learning, conversations, driverless vehicles, automatic fire control, swarms. So these are all things machines can learn to do. And there's a subset of AI, it's not all of AI. So with these interpretations, artificial intelligence going after intelligence, nobody really has any idea how to do this, and little progress has been made since the beginning of the field. On the other hand, machine learning has been, machines that learn have been very successful. They've made a lot of progress with that. So almost all recent artificial intelligence progress is actually machine learning. Most of the military applications that we come across are machine learning. So we don't have to have an answer to the general question of artificial intelligence in order to do machine learning. We can do that now, and we're getting better and better at it. Throughout the lecture series, you're going to be hearing about the Turing test. This was a test invented in 1950 by Alan Turing, who was one of the grand pioneers of computer science. He started to speculate, what does it mean to have an intelligent machine? And he said, nobody knows how to define intelligence, so what can we do with this? And he sidestepped the issue of defining intelligence by specifying what he called an imitation game. And the idea was that an interrogator, could talk either to a computer or to a human being, but you can't see who's who. And the question is, how long will the conversation go before you figure out which one is the human and which one is the machine? And the longer it takes, the more likely you would say the machine is intelligent. So that was the essence of the Turing test. So here's a little diagram showing what we were just talking about. There's a computer and a human hidden behind some screen that you can't see who's who, and there's an interrogator that can ask any question of either one of these entities, and the job of the interrogator is to figure out which one of those is which. So one of the questions is, how long does it take the interrogator to distinguish the computer from the human? And then that leads to another question that you'll frequently hear about is, even if you can't distinguish the computer and the human, both of them sound equally intelligent, is one of them simulating intelligence and is not really intelligence? Is the computer simulating something that looks to us like intelligence but really isn't? Philosophers have been debating about that. There's one philosopher named John Searle who has a simple example. He says, we can simulate digestion, but simulated digestion is not digestion. It doesn't absorb nutrients, it doesn't keep you alive. So if you want to stay alive, you have to have real digestion. So the same kind of question comes up here, is even if you can't tell the difference from the conversations about who's who, you still don't know whether you've discovered intelligence. There was a famous experiment done in 1966 by Joseph Weizenbaum at MIT. He wrote a program called ELIZA. And ELIZA was a very short program. I think it was around 200 lines, using keyword substitution to simulate a Rogerian psychotherapy session. So there's a branch of psychotherapy from Carl Rogers called Rogerian psychotherapy. So he was able to simulate a session. A lot of people who interacted with this program thought it was intelligent. And this reaction really surprised Weizenbaum because he wrote this program to show the Turing test wasn't really a good way to define intelligence or even to discover it. So he intended ELIZA to discredit the Turing test, and yet here's people finding, oh, this thing is intelligent. The next picture shows an example of a conversation going on with a ELIZA program. I'm not going to read this to you, but if you have access to the slides, you can look through it and read it and see the type of interaction that's going on here. And all it is when you say something, the ELIZA program grabs one of the keywords from what you said and gives you some sort of a question back or something based on that keyword. And that's, to many people, that sounded like a real conversation. They said this passes the Turing test. And that was exactly the opposite of what Joe Weizenbaum was trying to show people. So here's a little more of the conversation, but it's all the same thing. It's sometimes fun to read these things, and you can be surprised about how realistic some of these things sound, even though you know it's being generated by a machine that doesn't know anything. Well, the Turing test changed the question about a subjective interpretation of intelligence to an objective machine output question. So we can't observe intelligence directly, but we can look at how machines are responding and make assessments about whether it has an intelligence behind it. Well, it turns out that didn't help because it didn't inform us anything about how we're going to build a machine that passes the test. To this day, I would say up until about a year ago, people have been trying constantly, every year, trying to build better machines that would pass the Turing test, and nobody really got close. With the appearance of this new technology called ChatGPT, a lot of people started saying, this passes the Turing test. Not everybody was saying that, but a lot of them were saying it. So there's been a shift that happened recently because the machine got a little closer to having a human-sounding conversation than anything we'd seen before. Well, this also brings up another question. As we're talking about machines simulating intelligent or appearing intelligent, what do we mean by a machine? Well, normally with artificial intelligence, we talk about computers, computing machines, but some other fields have their own kinds of machines, and some of them wonder whether their kinds of machines are intelligent. Like if we build a driverless car, those of us who are computer scientists see computers at work there, so we can ask whether those computers are intelligent. Or if you're an automobile engineer, you might not care so much about the computers, you're worried about the whole car. And since this car is driverless, you might ask whether the whole car is intelligent in some way. So when we talk about machines, we usually mean something like an apparatus built of components, the purpose of which is to automate a process that we humans want done. And building the machine grants us an advantage, such as amplified force or speed, that humans don't usually have. Machines can operate on their own or depend on humans, so we would like to say humans are partially or fully out of the loop. And then a computer is a particular kind of machine with hardware components controlled by software, and its purpose is to implement input-output functions described by algorithms. So there's a number of different ways of thinking about machines, but there's always this sort of idea of basically of automation coming along with it. So this brings us to this question of what is the machine, brings us to what we call the hierarchy of learning machines, which is going to be the backbone of this series of lectures. A lot of our lectures are organized around exploring different levels of this hierarchy. So what we want to do is, there's a lot of different kinds of machines that look like they can learn things, which is what puts them in the domain of artificial intelligence and machine learning. And we want to classify these existing machines according to their learning power. So learn means acquiring a new capacity for action, and we can try and measure the capacity for action and compare machines' abilities and limitations and risks this way. And also we get a precise language for evaluating learning machines by talking in terms of a hierarchy of observable, measurable things. So this picture here just reminds us of what we're talking about when we say one machine is more powerful than another. So A is supposed to be a more powerful machine than B, which simply means A can learn functions, B cannot. So they're both learning machines. B can learn something, A can learn something, but A is more powerful than B because it can learn something that B can't learn. Well, when we do this and we look at the existing machines out here, here is a hierarchy that you can see. And we're going to talk about each of these levels here in the next few pictures, the next few minutes. So basic automation, level 0. Level 1 is rule-based systems. Level 2 is supervised learning. Level 3 is unsupervised and reinforcement learning. Level 4 is generative AI. Level 5 is human-machine interaction AI. And level 6 is aspirational AI. So let's take a look at this hierarchy of learning machines here. The first observation I'd like to make about it is levels 0 through 5 are different degrees of automation. These are all things that seem to, when they look intelligent, we all kind of agree they're simulating something that we normally associate with human intelligence. So we're not trying to claim they're intelligent. We are trying to claim that the aspect of intelligence, which we call learning, is being reflected here at each of these levels. Let's take a look, start here at level 0, which is basic automation. So we use this level 0 as the baseline for the hierarchy. It's really not intended to be intelligent at all, but it's a baseline for automation. So this is kind of classic. When we talk about classical automation, we've been doing this for years, long before computing came, and we're using that as a starting point here. So the idea is to get a machine to perform a process that we humans do. And once we get the machine to perform the process, we get ourselves out of the loop. We basically start the machine, performs the task, and then gets done. And so we've now got the task performed, but we didn't have to be personally doing it. The machine might have feedback to enable it to have stable operation, but the feedback doesn't change the function. It's a stabilizing influence, but it doesn't change the function. So there's no learning going on here. Machine learning could be used in some components of an automated system. For example, a driverless car has some machine learning components, but it also has a lot of other types of components that aren't artificial intelligence. But the whole point is that it's trying to drive the car from one place to another, ultimately without the human having to do anything. Examples of this type of automation are autopilots in airplanes, container shipping, robotic warehouses such as Amazon has introduced, and voice response robots, including the simple things, Alexis and Siri. These are all basic examples of basic automation. Level 1 is rule-based systems. See, these are computer systems, the program systems that make logical deductions. they start with an input, and then using rules and facts from a database, they try and reach logical deductions, conclusions from that input. Early examples of this are checker and chess. So we were able to write programs full of rules and basic facts about checkers or check. And an input might be a picture of a current chess board, and an output would be a recommended move. Expert systems, another form of one of these type of rule-based systems. Here now we're trying to get the system to perform like a human expert in a domain, like an expert doctor making a diagnosis, or an expert salesman making a sale, or an expert mechanic fixing an airplane or a car. So anywhere we could look around and find human experts, the idea was we want to find out what are the rules by which these human experts do things, put them into a machine, and then the machine will become equivalent to the expert. So examples have been medical diagnosis, image interpretation, equipment repair, logistics, and there's numerous other examples. Level 2 is supervised learning. So this is based on artificial neural networks. So the neural networks are networks of simple components that resemble the structure of a brain. And the idea is we're going to learn, the network learns a particular input-output function from a large set of examples. So we present example at the input to the network, we tune up the internal parameters, and until the output coming out of the network is the same as the input. Or actually, it's not the same. It's a label that we've provided for the input. So you have an image of a cat, and the word cat comes out. That's what we're trying to do. And so we show it the image of a cat. We train it by adjusting the internal parameters, and eventually the output will say CAT. So we now have a way of taking images and detecting the ones that have cats in it. So the idea here is that when we train the network, it now approximate a function, and because the approximation is possible, it gives an exact answer. So sometimes we can show examples of cats to our network, and it classifies them as dogs. So we can't guarantee they're actually 100% correct. So when we present an input that's not in a training set, you don't know. You may have some confidence that it's going to give the correct output, but we don't know for sure. And this makes reliable training data a real problem. It's finding good training data so that when we get done training the neural network, it gives good results even on data that has not been trained for. So we see this in working examples of image and speech recognition, language translation. We'll see all sorts of weird ways the network can go wrong. So the good thing about this is you don't have to figure out all the rules and program rules. You just simply present lots of examples of the input-output function. The bad thing about it is that because you don't have rules, you can't be sure that a particular output is good or bad. So level 3 is unsupervised learning. So supervised learning is called supervised because we've got training data, and the training data is driving the training process. The unsupervised learning tries to get rid of the idea of the training data and find some other way that the machine learns. So the idea is that we want to learn a function from the data without being shown examples. And one of the things this avoids is the sufficient data problem, which I was just hinting at, which how do you know how accurate your network is? Have I trained it with enough data? Do I need more data to get it to be more accurate? One early use of this, and still continuing use of it, is classification of unknown data into similarity groups or clusters. you still, the machine can say this group of things are all similar to each other, this group is similar, and so on. It doesn't have any meaning for this. The humans still have to look at the output and figure out what meanings to assign to those clusters. A very early example of this was a program written in the 1980s that would analyze star data collected by NASA telescopes and then group the stars into similarity classes. And astronomers found they made a few discoveries by looking at the data this way, discoveries they had missed by their own inspection of the data. So autoclass was seen as being helpful to astronomers. So this type of learning has been used for the game things, chess and Go, for example. The reinforcement learning is accomplished by having two copies of the machine playing against each other and knowing the rules of the game. So the two machines play a game, somebody wins, somebody loses, and the machine that wins reinforces its internal weight so that if that same situation came up again, the machine would be more likely to win. And for something where the machine lost, they decrease the weights of the connections so that the machine is less likely to make a move that leads to that bad outcome. And you do this for thousands and tens of thousands, 100,000, millions of simulated games, and the machine gradually gets better and better and finally reaches a high skill level. There was a machine produced by a company called Alpha Zero that learned to play chess and Go. And learning this two machines playing each other, they learned chess in 4 hours. When I say they learned chess, they were able to beat grandmasters that level. So this is up the Garry Kasparov's level. And then Go confirmed that it was a much harder game, but it only took 13 days to train that machine, and that's the one that beat the world master Lee Sedol. So in a way, this is a major breakthrough, is being able to do, like chess took 30 years using rule-based programming to get to a machine that would beat the grandmaster. And with this approach here, reinforcement learning, another machine did it in 4 hours. I think that's pretty amazing. Level 4, generative AI. This is the form of AI that suddenly appeared on our radars in November 2022. So these machines, these programs can create new texts, poems, pictures, images, music, art, and even code that are taken by humans as being creative. This is also known as GPT, as in ChatGPT, and large language models. So you hear all these terms. They're actually technically a little different from each other, but when you put them, most people they all mean the same kind of thing. So they're all powered by a monster artificial neural network. That's what when they say large language model, that's where the word large comes from, is a monster neural network. And the GPT-4, which is a program from the OpenAI company, has 1 trillion parameters in their neural network. That's a huge amount of parameters. It's trained from a text corpus of hundreds of billions of words pulled out of the internet. It took it 90 to 100 days of supercomputer time and $100 million worth of electricity to train it. So this monster machine is really, really expensive. However, once it's been trained, it gets answers in a matter of milliseconds. So given an input text to this machine, it's called a prompt, it generates an output text that is most likely to have been said somewhere in the training data. So we've got all this training data, billions of human documents are in there, and the prompt gets the machine to come up with a text string that's statistically similar to the one, or statistically correlated with the one at the prompt. Some people call this a stochastic parrot. Stochastic because it's randomness here, probabilities, and parrot because it's really repeating back to you what's already in the database, but it's being called forth by the prompt. One of the amazing things about these things is the first neural network machines capable of human-like conversations. So suddenly we have machines that can talk like us, and that changes everybody's relationship with those machines. So some of the promising uses here are customer service, chatbots, initial drafts of text and code, general provocations, jump-starting amusements. And there's been huge investments being made in this technology. It's also untrustworthy technology because the phenomena that are sometimes called hallucinations and fact fabrications are common, which means you put a prompt in, it generates an output, and then you do fact checking on the output and it's wrong. So it speaks authoritatively back to you, but it's just wrong. And so that's called a hallucination. There's nothing, nobody has any way to deal with that. It just, they say it's part of what you get here from this package. And there's also big concerns coming up now about intellectual property. People with copyrighted materials that are out there on the internet with copyright notices up, being scraped up and used to train ChatGPT-4. Now there's a whole bunch of lawsuits being made against the company. They're claiming they've used copyrighted material without permission. There's also fears of data pollution in the training sets, making these hallucinations more likely. And some people even worry about a threat to humanity as these machines can become progressively more intelligent as they train on more and more data, and eventually be smarter than machines, than humans, machines being smarter than humans, and implement one of those Hollywood Terminator scenarios. So level 5 is humans and machines interacting together. So here we're talking about a system designed with an interface that allows humans and machines to do what each is best at, producing a combined result that's better than any human machine can do alone. So the aim here is to amplify or augment human intelligence. Examples are freestyle chess, which is a form of chess invented by Garry Kasparov after he was beaten. He said, hey, we're going to have a new kind of chess tournament. Every player can bring a computer with them, which has a chess program on it, and use that as an advisor. And that turned out to be very popular, and a good chess player in a good program could beat the supercomputer. So that was an example of machines interaction. So this is a big research area now, how to try and build these interfaces that bring humans and machines together in this way. The highest level in that hierarchy is aspirational AI, nowadays called artificial and general intelligence, and these are supposedly machines that would be able to do anything intelligent a human could do. So this is the ultimate goal of AI research, sometimes the holy grails, but to date nothing like this exists. In fact, no one knows how to do them at all. And there's been endless debates on whether such machines are even possible. Well, in the context we work here, this is an interesting intellectual question, but is not much practical question. No military artificial intelligence depends on aspirational AI. It's all machine learning. One of the problems that these machines have is, we call it the context problem, the idea is that to bring learning machines closer to human intelligence, we need a solution to this problem. Context is the word we use for the human ability to sense issues that are unstated in the background of experience, and then bringing them forth to give meaning to what's around us. There's a famous AI project called Psych, which spent 40 years developing a database of 30 million common sense facts, which were supposed to help expert systems become experts by being able to sense context. And unfortunately, this didn't help. Expert systems never got to be experts. So machines don't sense context. And a simple explanation for this is they're made of components, they interact together, but they're all local components. Each component only depends on its neighbors, doesn't depend on anything going on at a distance. If something's going on at a distance, it has to be transmitted through a chain of events until it becomes a neighboring signal. So context means that these machines don't understand the meaning of any input or output. You can say all the components are context-free, and at the same time, this turns out to be a gigantic benefit because this is what allows these machines to run very fast. So until we can formalize this idea that bringing forth something from the context, there's no way the machine can do it. I want to wrap up this discussion here with 4 things about cautions, hype, anthropomorphizing, overbroad definitions, and master algorithms. When you hear people talking about artificial intelligence, they're likely to bring one or more of these up. So hype means over-exaggerating. It turns out this is a common bad habit of people claiming more than the machines can deliver. And there's even a hype bandwagon which people try and drop the term AI liberally into all their presentations and proposals so as not to be left out of the game, even when AI has no known technology to help them do what they're discussing. So this is a problem. There's been a lot of exaggeration, and we're hoping through this lecture series and through the definition of a machine's hierarchy to show you how you can evaluate what's going on without falling into the hype trap. Closely related to it is anthropomorphizing, which is a tendency to attribute human attributes of intelligence to machines, even though we don't know whether machines are actually intelligent. So we do this all the time in an informal way. So we say the computer is an electronic brain. The computer knew where I was. The computer thought the input was wrong. The computer understood my problem. But it's not a brain, and it doesn't know anything. It doesn't think. It doesn't care. It doesn't understand. So we still talk about it as if it does, but this problem of ascribing human qualities leads to this issue of, it actually accelerates hype, because if you actually believe the computer knows something, you may say, I'm going to deliver a product that knows something, when actually you can't do that. Here's a list of things that machines and humans can do. This is something, when you look in the backup, you can read these things. You see they're really different lists, and humans have different capabilities from machines when you look at this. I'm not going to dig into it. I think most people understand it already. Third area of caution is these overbroad definitions. So for example, AI's machines with the ability to perform functions normally considered intelligence. And in fact, most of the machines we have, nobody actually claims they're intelligent, but we still build them. They're good at machine learning. So as we said before, there's no agreement on what functions a machine has to be intelligent. Some people maintain that all human functions are intelligent, and therefore a human-developed machine or artificial intelligence all the way back to time immemorial. Well, that's not very helpful. It's saying every machine we ever built is an artificial intelligence, and that doesn't wash with a lot of people. Other people maintain that machine functions, by virtue of being functions of a machine, can't be intelligent. So you go in both directions. Somebody says everything is intelligent. Somebody else is saying nothing is intelligent. And some people claim that all software is artificial intelligence software now. 2 years ago, we just called it software. Now we're saying it's artificial intelligence. And that's not true either, because a lot of software that we use is not artificial intelligence. Fourth issue is the master algorithm, which is sort of a belief that this deep learning technology is going to eventually be the master algorithm that can do every AI function. So Alan Turing, the pioneer we mentioned before, one of his famous theorems was there can be no such thing as a master algorithm. It's theoretically impossible. So the idea that deep learning could become a master algorithm already violates one of the ideas of computer science. So deep learning is also level 2 in the hierarchy, and there's many more powerful kinds of machines above it. There's also a related claim to this that tries to belittle stuff that wasn't actually built by artificial intelligent people by saying all of that, all the systems and programs we have were handcrafted, built by ad hoc methods. Well, the engineers who built them using formal verification of logic would not agree with that. And in fact, many of the pre-AI systems are very well engineered, and today's deep learning systems are actually handcrafted if you take a look at the way they're built. And another one of these things you got to watch out for. So the best way forward here, anyway, is making careful assessments in each case that you're working in about whether AI can help a military system by looking at the requirements and evaluating the machines, the algorithm, and the data to see whether they actually realize the environments. And the other related question is what machines of the hierarchy and what other machines must be combined to do the military job. And that is the end of what I wanted to say. So we leave you to the rest of this series of lectures. We have 21 more experts in here to tell you about individual things that are being done with this technology. And we hope that you will enjoy all the dimensions that they are going to show you and what you learn from them. So thank you very much.